Adarsh, can you check whether there is any issue with the link? Few of them have messaged that they are not able to join. Adarsh,
Yes, sir. Just a
can you
minute.
please check?
Sure, sir.
Sir, can you start from 7-5?
Yeah.
Okay, sir.
Good evening, sir.
Good evening, madam.
Good evening. Good evening, Dr. Anand.
Good evening, sir.
Yeah, I am Muhammad Qasim, the Vice Chair of IEEE Kerala Section and Founder Chair of Education Society. Nice to see you.
Nice to talk to you, sir. Thank you.
Hello, everyone. I hope I'm audible and visible. Right?
Yes,
You are audible. Yeah.
Okay, so good evening, everyone. I extend my heartfelt greetings to all the dignitaries and delegates in attendance. The universe is vast yet infinite. It is beautiful, but it is mysterious in more ways than we could possibly imagine. Every object in space, be it stars, planets, or galaxies, have certain positions related to one another. But mapping those positions is entirely different from how we map places on Earth. So, to provide an insight into how astronomers put together a map of the universe by compiling years of meticulous observations, IEEE ETSO Kerala chapter is here with the webinar Mapping the Universe in 3D. The session will be handled by Dr. Anand Narayanan, who is a professor in the Department of Earth and Space Sciences at the Indian Institute of Space Science and Technology, Trivandrum. So, to get the ball rolling and to have an auspicious beginning to our session, I would like to invite Dr. Rajesh Joseph Abraham, Joint Secretary of IEEE ETSO Kerala chapter, for the welcome address. Over to you, sir.
Good evening and welcome you. I welcome you all to this session. Ladies and gentlemen, dear student participants and other registrants. So we all make use of Google Maps and other such facilities these days to travel from one place to other. So mapping the universe in 3D is a tedious task, and the presenter for today is Dr. Anand Narayanan. Dr. Anand Narayanan obtained his BTech in Electrical Engineering from College of Engineering, and afterwards his MS and PhD degree in Astronomy and Astrophysics from Pennsylvania State University, USA. Since 2011, he is with IEST, where currently he is serving as a professor. So I welcome you, sir, to this session. I also welcome all other delegates and participants to this session. So with these words, let me not stand between you and the speaker. So I welcome you all once again, and over to you, Dr. Anand Narayanan.
Thank you. Good evening to everyone who has tuned into this webinar. Thank you, Dr. Rajesh Joseph Abraham, who is also my good friend and colleague at IIST, for giving me this opportunity to interact with all of you this evening. And a special thanks to Akshay for putting together a nice, concise, beautiful introduction to the topic that I'm going to be talking about. So without ending much time, let me start sharing my slides. So if one of you can just confirm whether the slide is visible.
Yes, please.
Yes.
Thank you. Yeah. So before I begin, I just want to mention that since this is an online talk, we are at the mercy of technology. So if for some reason, if my internet connectivity gets disrupted, please do bear with it. I will reconnect within a few seconds. Okay, so as it was mentioned in the introduction, what I'm going to be talking about today is one of the most ambitious projects that has happened in the domain of astrophysics, in the field of astrophysics, in the last 30 years or so, which is to come up with a 3D architecture of the universe, a 3D map of the universe. And what we are looking at here in this particular slide as a broken piece of slab is the oldest discovered map of the world. In Latin, this particular historians refer to this as imago mundi, which means image of the world. And archaeologists tell us that this particular map, this particular clay tablet was made by ancient Babylonians about 2,500 years ago. And this was discovered in a small town in Iraq, north of the ancient city of Babylon, along the fertile banks of the Euphrates River. And this particular map, which was made by our ancestors, human ancestors 2,500 years ago, it shows the earth and the heavens as seen through the imaginative eyes of the Babylonians themselves. Okay? And the reason why I thought this would be a good starting point for today's presentation is because maps have always been an integral part of human exploration of the world around us. Humanity's course through history, if you look at it, it is intimately intertwined with maps like these. And these maps are not just diagrams, they have always been a very essential part of human exploration. They tell us the story of our understanding of the world in a very simple visual way. And most importantly, these maps help us to see how we are connected with a larger scheme of things, with the rest of the things around us. So today's presentation is also a story about map making. It is a story of cartography. But it's not just any kind of cartography, but as I mentioned, it is probably one of the most ambitious map-making exercises that humankind has ever undertaken, which is to map our universe itself, our entire universe itself. And this is a field where there is a lot of progress that has been happening in the last 2 to 3 decades. And it has resulted in an ever-growing understanding of who we are and where we are positioned in the entire universe, if you look at it at a larger scale. So this is a small animation of the night sky. Depending on how well it is getting streamed, you may be able to see the starry sky moving from one end of the screen to the other. So when we look up at the night sky, which is the laboratory for astrophysics, when we casually look at the night sky, it looks like the stars that we see in the night sky, they are spread out in a more or less random fashion. It looks like the stars are randomly sprinkled in the sky. But we know that that is not really the case. The universe isn't a random jumble of objects. It has a structure which is composed of galaxies and a lot of material in between those galaxies. And what we are going to discuss in the next 30 minutes is how astronomers have very carefully put together the 3D map of the universe through long years of very careful, very painstaking observation. So if you want to know what is the 3D architecture of the universe, another way to phrase that question, another way to frame that question is how matter is organized in the universe at large physical scales. Okay? At the largest possible scales that we can measure, how is ordinary matter, matter that is made of atoms, protons, neutrons, electrons, etc., how is it organized at large scales? So let's begin that journey of understanding how matter is organized at large scales by looking at our own galaxy, the Milky Way. So this is a photograph of the night sky taken by a friend of mine from ISR Trivandrum, in a place called Vithura in Trivandrum, which is not far from IIST. So he took it with the help of a DSLR camera, a long exposure image. And you can see countless numbers of stars in the sky. Okay? Images like this remind us that we are living inside a galaxy. Our sun, the star around which we are orbiting, all the planets are revolving, the sun is a part of a huge collection of about 200 billion stars. And this gravitational assembly of 200 billion stars is what we refer to as the Milky Way galaxy. And we are embedded inside the Milky Way galaxy. And whenever we look at the sky, whatever stars we see with the naked eye, they are all stars that belong to the Milky Way galaxy. Suppose if we could travel at very large speeds, hypothetically speaking, suppose if we could travel in a spaceship at speeds close to the speed of light, and if we could come out of our galaxy, okay, then this is what we would see. This is how all the 200 billion stars in our galaxy is assembled. So this is a view of our galaxy from outside the galaxy. Now, I don't need to tell you that this is a computer visualization because nobody has actually gone out of our galaxy. No spacecraft has gone out of the galaxy. The reason is because of the enormous distances that we are talking about here. I mean, it's impossible to exit our galaxy in a reasonable time frame. But by carefully mapping the position of stars within our galaxy, we know what roughly our galaxy would look like from outside. And it looks like a disk galaxy. Okay, so this is a disk. Our Milky Way is a disk galaxy as seen in this animation. Let me play that animation once again. It has a disk-like structure, and within the disk, there is a spiral pattern. So many of you they would have read in popular science books that the Milky Way is a spiral galaxy. So that's how our universe looks in its local neighborhood. And we know that Milky Way is not the only galaxy in our universe. Our universe has millions of galaxies in it. The nearest galaxy to the Milky Way is Andromeda galaxy. Okay, so we are now exiting our galaxy and we are trying to look at similar star systems in the local universe. So what you are seeing here in the center is the Milky Way galaxy running from left end of the screen to the right end. And this video is going to zoom in into a small region that is on the southern galactic hemisphere. And there you will see Andromeda galaxy. Okay? That is the location of Andromeda galaxy, which is what this video is zooming into. Now, Andromeda is a galaxy in itself with more number of stars than Milky Way. But if you look at it through a telescope, Andromeda looks like a very tiny object, or with a very good pair of binoculars. During the month of October, November, December, if you look in the western part of the sky after sunset, if you know where to look, you can see Andromeda galaxy. It looks like a tiny smudge, even though it is a galaxy in itself. And the reason why it looks like a tiny smudge is because of the enormous distance that separates us from Andromeda galaxy. So this is a picture, what you're looking at in the slide is a picture of Andromeda galaxy taken with a big telescope. With a pair of binoculars or with a small telescope that some of you may be probably having, we will not be able to see Andromeda galaxy in this level of detail. Okay? This requires much more sophisticated instruments. So this is a photograph of the Andromeda galaxy, and Andromeda is at a distance of 2.5 million light years from us. Now, as all of you probably know, because the distances in astronomy are so large, we don't usually refer to the distances in meters or kilometers or miles. Instead, we use this unit called light year, which is the distance that light travels in 1 year, which is roughly 10 trillion kilometers. Okay? To put it in another terms, if you take a light particle, a photon, in 1 second, a light particle can go around the Earth 7 times. 300,000 kilometers in 1 second. That is the speed of light. Traveling at that speed, light takes 2.5 million years to reach us from Andromeda galaxy. So that is how far away Andromeda is. And Andromeda is the closest galaxy to the Milky Way. So now you understand that even words like nearby or close have a completely different meaning once you start talking about objects in outer space. Now, Andromeda is not the only other galaxy in the universe. There are many galaxies in the universe. So what you're looking at here is a Hubble Space Telescope image, a panning of the Hubble Space Telescope image that shows that is showing many galaxies. So every object that you are seeing in this visualization is a galaxy in itself with billions of stars in it. Let me play it once again, that video. So wherever we look in the sky, if we look deep enough with our telescopes, we are able to see star systems like galaxies. And very much like human beings, we don't tend to, we don't always like to be alone. We try to hang out with other people. In the same way, galaxies also always do not exist in isolation. Many galaxies form clusters and groups. So this is actually an image taken with the help of a telescope and a CCD camera connected to the telescope. In this image, every extended object that you are seeing, okay, so I don't know whether the mouse pointer is visible, but every elongated object that you are seeing is a galaxy in itself, and they are all roughly at the same distance from us, and they form a gravitationally bound entity, which is called a galaxy cluster, the group of galaxies, and this particular one is called the Virgo galaxy cluster. There are probably 1,000 or more galaxies in this Virgo cluster. So now we know that not all galaxies exist in isolation. Many galaxies, because of mutual gravitational forces, they tend to form groups and clusters. Okay, so there is some hierarchy to structures that are present in the universe. Here is another image of, here is an image of another galaxy cluster. This is called the Coma cluster. This particular image is taken by the Hubble Space Telescope. Every single object that you are seeing here with a yellowish hue, that is a galaxy in itself at a very large distance from us, which is why it is looking very small. And they are all at roughly the same distance from us. They are co-spatial and they are gravitationally bound together to form a structure, which is called a galaxy cluster. And this is the Coma cluster. So similar galaxy groups and clusters are seen throughout the universe. Okay, our own Milky Way galaxy is part of something called the local group. Okay, we also have some neighboring galaxies which forms a gravitationally bound entity called the local group. Now, the challenge, so if you now keep on doing this, if you keep on identifying galaxies and clusters, etc., then the question is, at larger and larger scales, how does this organization of matter, how does this organization of galaxies look like? Now, it's not an easy question to find an answer to. And the reason is because if you go out and look at the night sky, the sky looks like a hemisphere to us. Okay? The sky looks like a dome-like structure to us. And so it looks like a 2D surface. The night sky looks like a 2D surface. And on the surface is where we see all the stars, galaxies, planets, etc. So it's very easy to tell where an object is in the sky. But it's very difficult to tell how far away or how close an object is to us. Distances to these objects is very, very difficult to determine. We can easily tell whether an object is in the northern part of the sky or northwestern part of the sky or southern part of the sky or eastern part of the sky. The coordinates of these objects in the two-dimensional sky, we can easily measure. But to know whether an object is 100 light years away from us or 1,000 or a million or tens of millions of light years away from us, that is a much more difficult measurement to do. But that's a very important measurement because if you want to make a 3D map of the universe, we need the 3 coordinates that define the position of an object in 3D space. One is the 2 coordinates where the object is in the sky. The other is how far away or how close the object is. So knowing distances is very extremely important if you want to know the 3D architecture of the universe. Okay. So how does our universe look in 3D? One way to answer that question is to find out how galaxies are organized in the universe. What are their positions in the sky and how far away and how close they are to us. Okay? Distances to these galaxies also. So do a large survey covering as many galaxies as possible and try to determine their positions and their distances. This is the approach that astronomers have taken to understand the topology of the universe, the topography of the universe. So how are distances to galaxies estimated? Now, there are multiple ways to establish distances to galaxies. I'm going to talk about one of the most frequently used method. okay, on how distances to galaxies are determined. So on the left-hand side, what you are seeing is an image of a galaxy, a photograph of a galaxy. This galaxy probably has millions of stars in it, but it's looking very tiny because it is very far away from us. On the right side, what you are looking at is a spectrum of that galaxy. Now, most of you would be knowing what a spectrum is. In school, we have all done this experiment where we take white light and when we pass it through a prism, a glass prism, the light that comes out of the other side, it will have this rainbow of colors. Okay? So what the prism is doing is it is dispersing the light, it is spreading the light into its component colors or component energies. So this rainbow of colors that we see on the other side, we call it the spectrum of the white light. In the same way, the right-hand side image, it is obtained, the right-hand side graph is obtained by collecting the light from the galaxy with the help of a telescope and sending it to a spectrograph. The spectrograph will have a dispersing element like a grating or a prism, and that grating or prism will spread the light into its component wavelengths. So those wavelengths are written in the x-axis, the horizontal axis of this graph, and vertical axis is the brightness at each wavelength. So you can see that the wavelengths go from 4000 angstroms to 9000 angstrom. That is the visible part of the electromagnetic spectrum. Okay? What we see is the visible part of the electromagnetic spectrum, what the human eyes perceive. And that is exactly the wavelength that is written here. And when you look at the spectrum of this galaxy, you can see that there are some lines that are going up and there are some lines that are going down. These lines are produced by chemical elements, by atoms that are present in that galaxy. So some of these lines are produced by hydrogen atoms, some of them are produced by sodium atoms, some are produced by helium, some are produced by sulfur, etc. So that is what is marked against those lines. So different chemical elements will produce different lines. And these lines always occur at very exact wavelength. For example, the sodium lines will always occur at around 5860 angstroms. That is what gives the sodium vapor lamps their yellow color. Okay? Because sodium atoms emit light at 5860 angstrom. Similarly, hydrogen atoms, the Balmer series of hydrogen atom, the hydrogen Balmer alpha transition happens at 6560 angstroms roughly. So there are specific wavelengths at which these transitions happen. Now what happens is, if the galaxy is moving away from us, then the entire spectrum will shift towards lower energies. This is called Doppler effect of light. A sound also exhibits Doppler effect. If an object that is emitting sound is approaching us, then the pitch of that sound will increase, the frequency of that sound will increase. And if that object that is emitting sound is receding from us, is moving away from us, then the frequency of sound will decrease. The same way for light, for electromagnetic waves also, something similar happens. When a source that is emitting light is moving towards us, the entire spectrum of that object will shift towards higher energies. And if it is moving away from us, the entire spectrum will shift towards lower energies. We call this blue shift and red shift. Okay? And as it turns out, the shift in wavelength is a very useful measure of how far away a galaxy is. Mostly, galaxies in the universe exhibit redshift. So sitting here in Milky Way, if you keep looking at galaxies, we will find that their spectrum shows a systematic redshift. And that means that those galaxies are receding away from us. And this is true for most galaxies. Almost all galaxies in the universe, they exhibit a redshift. And this redshift is a proxy for distance. Higher the redshift, farther away the galaxy is. This fact is very well known in astronomy. And so astronomers, they measure the spectrum of a galaxy. And from the redshift that they see in the spectrum, they determine how far away the galaxy is from us. So spectroscopy, recording the spectrum, is a crucial step involved in determining the distances to galaxies. So once we know the distance, we know the position of the galaxy in the sky, we can make a 3D map of the universe by putting all the galaxies at respective places wherever they are. So this is the approach that galaxy surveys have used. And for the rest of the talk, I'm going to be talking about one such very ambitious survey that started in 2000, the year 2000, and it was more or less completed in 2008, but it is still ongoing. Okay? And the survey is called the Sloan Digital Sky Survey. For short, it is called SDSS, Sloan Digital Sky Survey. This survey, as I mentioned, it started in 2000, and it was the survey was done with the help of a telescope, and that telescope is what you are seeing in this picture. This telescope is located in a state called New Mexico in North America. So this is in the northern part of our equator. About the latitude of that location is about 32 degrees north of equator. That is where this observatory is. The observatory is called Apache Point Observatory, located in New Mexico in the northern hemisphere. And that telescope has a primary mirror that is about 2.5 meters in diameter. And it has a focal length that is 5 times larger than that. Okay. And this particular telescope was what was used for the Sloan Digital Sky Survey. Over a period of 8 years, the Apache Point Observatory SDSS telescope took images and spectra of more than 2 million galaxies in the universe. So 2 million is 2 followed by 6 zeros. Okay? 2 million galaxies. It very carefully took images and spectra of all these 2 million galaxies, and using that, astronomers could reconstruct a 3D map of the universe. Now, since many of you are from the engineering background, let me briefly talk about the engineering behind the construction of the telescope and the recording of this data. So how SDSS does, Sloan Digital Sky Survey does its observations is, the telescope has a field of view of roughly 3 degrees. Okay, so 3 degrees means in a single pointing, it will be able to look at a patch of the sky that is 3 degrees across. Now, just to put that number in perspective, a full moon is roughly half a degree across in the sky. So that means SDSS in a single pointing, it will be looking at a region that is 6 times the size of the full moon. That is the field of view of the telescope. So in a single pointing, it will look at 3 degrees, and then it will take an image of that region of the sky. So this is one such image taken by the Sloan Digital Sky Survey telescope. And every object that you see here is emitting light. Some of them are stars within our own galaxies, our own galaxy, the Milky Way. Some of them are galaxies that are outside of the Milky Way. So what astronomers would do is they will take an image of the patch of the sky like this, and they will identify which objects appear to be galaxies. So visually, they will try to confirm. There are some algorithms also that are used in image processing to identify interesting objects in this image. And then, as a follow-up observation on a successive night, they will try to record the spectrum of each interesting object in this field. Okay, so now remember that this is just one pointing of the telescope, and already you can see that in one pointing there are so many objects. There are probably hundreds of interesting objects in this field. Now, if you go and record the spectrum of each object one after the other, then the survey is going to take a very long time. It's a very inefficient way of doing things. This is where engineering comes into picture. Advancements in optical design, optical engineering, advancements in control systems, etc., have helped astronomy in many ways. And one such contribution is what I'm going to talk about. So what SDSS does is, instead of recording the spectrum of every galaxy one after the other, it tries to record the spectrum of hundreds of galaxies at the same time. Okay? And the way it does it is, SDSS uses an aluminum plate like this. So you are looking at a aluminum plate here. This aluminum plate has a diameter of about 80 centimeters. And you can see that there are many small pinholes that are punctured in this aluminum plate. So every pinhole here would correspond to the position of an interesting object in this field. So SDSS will take a picture of the night sky. Astronomers will identify interesting objects in that picture, and then they will take an aluminum plate and then they will puncture holes in this aluminum plate corresponding to the locations of those interesting objects in that field. And this aluminum plate is mounted at the focal plane of the telescope where the light is collected. Now, why are these holes punctured? Because every hole is then connected with an optical fiber. So an optical fiber is manually inserted into each of these holes. So in a sense, each hole will be looking at a particular object in the sky. When the telescope again points at that same patch of the sky, every hole, like a pinhole, it will be looking at a particular object. The light from the telescope will be collecting the light will get focused on the focal plane, and the hole, through that hole, the light from that object will come, and the optical fiber will collect that light, and with almost near zero loss, the light will be sent to a spectrograph. And the spectrograph would disperse the light, it will spread it into its component colors, and the spectrum will be recorded by a wide field CCD camera that is connected to the spectrograph. So in one pointing, the telescope will be able to simultaneously record the spectrum of nearly 600 galaxies that are present in a single image like this. So right now I'm going to show you a video of how this is done. So what you are looking at here is an aluminum plate, and the holes are punctured not manually, but with the help of a robotic arm. The tip of that robotic arm has a ruby crystal in it. A ruby tipped probe, and that goes and punctures the hole in the aluminum plate. The hole is only about a few micrometer in diameter. Okay, that's pretty much the diameter, the size of these holes, pinholes. And every aluminum plate usually has about 600, roughly about 600 holes. And then an optical fiber is manually inserted into each of these holes. So you are looking at a time-lapse video of somebody sitting and inserting optical fibers to each of these holes. So until recently, this job was done manually, but recently with upgrades, a robotic arm does this insertion of optical fibers. Okay. This technique is called fiber-fed multi-object spectroscopy. Okay. So what this word means is you are recording the spectrum of objects, and you are not doing it one object after the other, but you are trying to record the spectrum of multiple objects, several hundreds of objects at the same time, hence multi-object spectroscopy. And how is the light collected from the focal plane and fed to the spectrograph? It is done with the help of optical fibers. So therefore, it's called fiber-fed. The fibers are feeding light onto the spectrograph. So what you are looking at here is the backside of the Apache Point Observatory SDSS telescope, and behind that you can see the aluminum plate ready to be loaded on the backside of the telescope, and down below you can see the optical fibers also. Okay. So this cartridge, these are called cartridges. These cartridges are loaded every night, and with the holes punctured in it and optical fibers connected to it. And once the cartridge is loaded, the backside of the telescope looks like this, the image on the right. You can see two green sections. Those are the two regions where the spectrograph is kept. So the optical fibers, they collect the light from the focal plane and they feed it to these green regions where the spectrograph is present, and the spectrograph records the spectrum. Okay, produces the spectrum, and the CCD camera records it. So here is a nice time-lapse video that shows the Apache Point Observatory, the Slow and Digital Sky Survey, getting ready for an observation on a given evening. So close to sunset, an astronomer would go and they will load the cartridges to the telescope. So this is the backside of the telescope. They remove the cartridges from the previous night and they load the new cartridges corresponding to the locations of objects that they want to observe that particular night. This exercise is repeated every night, and once sunset happens, the dome retracts, and then the telescope is ready for observations. Okay. So for over a period of 8 years, night after night, the Slow and Digital Sky Survey telescope has been surveying the sky, trying to take images and then follow it up with fiber-fed multi-object spectroscopy, trying to record the spectra of millions of galaxies. And at the end of 8 years, SDSS produced a 3D map of the universe. And what you are going to see now is a visualization of that 3D map. So every object that you see here that is passing by is a galaxy in itself with billions of stars in it. And this map has been produced with the help of data from the Slow and Digital Sky Survey. This computer visualization is showing how it would look like if we could fly through these galaxies and see the overall distribution. They all look like points because SDSS wants to convey that these galaxies are at large distances from us. So our own Milky Way galaxy is one small smudge like this. And in some regions, you can see that many galaxies are clustered together. So those are really dense galaxy clusters. In some other regions, the number of galaxies are lesser. So those are galaxy groups. And in some other parts, there are galaxies existing in isolation in space. Okay. So this is a video flyby of the SDSS map. Let me show you a static map of the same. So this is what a static map of the 3D map of our universe looks like. Let me explain what you are looking at. So you are seeing a circle, and then at the center of the circle, that is where we are. That is where Milky Way is. So our observation is sitting inside the Milky Way for we. So we are the center of this observation. And this outer circle, that corresponds to a distance of roughly 2.5 billion light years. 2.5 billion light year means 2.5 followed by 9 zeros. So that is how deep the Slow and Digital Sky Survey observations have been. And you can see that there are two wedges where there are a lot of fine data points. And there are two wedges where it is dark, black. So these two black wedges correspond to the region of the sky where SDSS did not do any observations. So SDSS did not do a full sky observation. Sitting in New Mexico, it could only observe about 1/4 of the entire sky. Roughly 14,000 square degrees of the sky is all that SDSS could observe. So that is why some parts of the map are empty, a blank. Now the region where data was collected, that is these wedges. And these wedges, you can see some green and red colors. Those just represent different types of galaxies. The reds represent elliptical galaxies, galaxies that have elliptical shape, and the green represents galaxies that have spiral shape, like the Milky Way. Those details are not important, but what you're seeing here is basically a collection of fine dots, and there are about more than 2 million dots in this picture. Each dot corresponds to a position of the galaxy in 3D space. So the 2D space is what you are seeing as the markings on the boundary, and the distance from us is the third information, is the third axis of that 3D. And so you're looking at a 3D map of the universe, a slice of that. And you can clearly see that how matter is organized in its largest physical scales. There seems to be regions where there are a lot of galaxies, where there are dense concentrations of galaxies, and there are regions which are voids, that are devoid of any galaxies. It seems like a nice network of filaments and sheets, and this is the 3D map of our universe. This is how matter is organized in large physical scales. And astronomers call this the cosmic web because it resembles the spider's web, okay? Where you have these filamentary and sheet-like things, a network of things jumbled together. And so therefore this kind of a map is also called a cosmic web. Now, so the takeaway is that from these kind of surveys is that now SDSS is not the only survey. Along with SDSS, there have been similar very interesting surveys done with other telescopes located at other parts of the Earth, and they all show the same results. Okay? They are all looking at different galaxies, but they all show this very similar maps. And the final conclusion is that the galaxies in our universe, or the matter in our universe, is not distributed uniformly, neither is it distributed randomly. Instead, the distribution has a pattern, and it is a web-like pattern. So what do I mean by uniform distribution? If the galaxies were all distributed like this, if every red dot was a galaxy, then this would be a uniform distribution. If the galaxies were thrown randomly in space, if they are positioned randomly in space, then the second image is how it would look like. But SDSS and similar surveys are showing that it's neither uniform nor random, but in fact there is a filamentary structure to the distribution of matter in our universe.
So at 10:30 we'll have Mr. Hardik Modi, and then at 11:00.
Now, how this filamentary structure came about from the early conditions that prevailed in the universe is a subject of very active investigation. How did this cosmic web structure come into existence? Now, probably many of you would know this from reading popular science books, that there are multiple lines of evidences that seems to suggest that our universe had a beginning roughly 13.7 billion years ago. This is what astronomers refer to as the Big Bang. Now, in the 100,000 years that followed Big Bang, the distribution of matter in the universe was more or less uniform. So, from a nearly uniform distribution of material, how did this web-like structure come into existence? So, this is a topic of very active investigation. Now, since the time scales involved are very large, we are talking about what happened in the universe 13 billion years ago, and what has been happening throughout the history of the universe for the last 13 billion years. Clearly, there is limit to which we can observe these things. In a human lifespan or in several generations of human lifespan, we cannot witness this structure formation happening. Therefore, what we have to do is we have to get the help of computer simulations. So, theoretical astrophysicists, they use computer simulations to try and understand how matter organized itself in the universe following 13 billion years of cosmic evolution. Okay? And these computer simulations, they start with some initial conditions. There are observations that show that the early distribution of matter in our universe was more or less uniform, except that there were tiny density inhomogeneities in the universe. There were tiny density fluctuations in the universe, in the early universe. So what I mean by density fluctuation is that there were some regions that were slightly over-dense compared to some other regions. Now, if that kind of a condition prevailed in the early universe, then the simulations show that, I'll show you the simulation in a minute. Then these computer simulations show that under the influence of gravity, it is very well possible for matter to start accreting together, coming together to form galaxies and galaxy groups and galaxy clusters and the large-scale structures that we see in the universe. So what I'm going to play now is a computer simulation that was done by a group at Max Planck University, Max Planck Institute for Astrophysics, where they have tried to simulate the universe from its early years to the present. And what you're looking at here is a snapshot of how matter was distributed in the early universe. You can see that it is more or less uniform, except there are some regions which are black, which correspond to regions which are slightly underdense. And there are some regions which are slightly overdense. And as this number that is written on top, it is written Z is equal to 20, as this number comes down, we are looking at time passing by. Okay. So starting from an early universe to the present, let's see what happens with the passage of time. As these computer visualizations show, the underdense regions become more and more underdense, and they evolve to become voids, empty space. And the overdense region, their gravity assembles matter together over large time periods of billions of years to form galaxies and large scale structures. So when we finally come to the present universe, which is Z is equal to 0, these simulations reproduce the cosmic web-like structure that we see through observations of galaxies, like what the Slow and Digital Sky Survey showed us. I'll play this animation once again. So early universe, more or less uniform conditions, except for tiny density fluctuations. Then gravity overtakes or gravity takes over the show, and over a period of 10 to 13 billion years, under the influence of gravity, matter starts to assemble to form these filamentary and sheet-like structures that we refer to as cosmic web. So at the intersection of each of these filaments, wherever you are seeing these bright knots, those are regions where there are many galaxies forming clusters, etc. So that's all I wanted to present, and I just want to leave you with a very interesting image. Okay? On the right-hand side, what you are looking at is the cosmic web structure, okay, from one of the simulations. So this is a numerical simulation, a supercomputer simulation of how structure formation is, or how matter is organized in the present universe. It very much looks like the SDSS map on the right hand side with filaments and sheets. And on the left hand is a image of the cerebellum part of the human brain. Okay? Cerebellum is a structure in the back side of the human brain. It contains more than 50% of the nerve cells or neurons in our brain belong to the cerebellum, although it occupies only a tiny part of the human brain. And this is an electron microscope image, what you are seeing on left. And the reason why I thought it will be interesting to show this is because of the similarity in structure that you are seeing here. Okay, there is some likeliness to the way nerve cells are interconnected in our brain and how galaxies are interconnected in the large scale structure of our universe. So one, we are looking at a very, very microscopic scale on how matter is organized, and on the other, we are looking at a very macro scale, at the scale of the universe, how matter is organized, and there seems to be some similarity. Now, I'm not saying that these two are connected in some way. Obviously, the nerve connections in our brain has happened because of chemical bonds, because of chemistry, and the large-scale structure of the universe is largely driven by gravity. But this is a very interesting comparison because it shows how very diverse physical chemical processes can result in building of very similar structures characterized by similar levels of complexity and similar levels of self-organization. So what is inside our brain, the way things are organized inside our brain is also how the universe is networked. And so this is very interesting thought to end this presentation with, and this is a vast topic, and I have just tried to give you a very superficial, a very peripheral overview of it. If you are interested to know more about this whole activity to map the universe in 3D and understand our own place in it, then this is a very interesting, accessible book. This book is written by an astronomer called Richard Goat, and it's called The Cosmic Web. It is available on Amazon, so if you're interested, you can go and read this book. And with that, let me stop the presentation and let me hand it over to the organizers.
Sir, thank you, sir, for your really great session. I really enjoyed it, and I'm sure all the participants have found it useful as well as insightful. And before we get into the Q&A session, let's take a virtual photograph. So I would like to request you all participants as well as professional members, to turn on your cameras and put a beautiful smile on your face. So could everyone please turn on your cameras?
Okay, I should say it before that only the first, let's say 1, 2, 3, 4, yeah, I think it's around 30 members. Only the first 30 who turn on the camera will get the picture. Okay. We have 80 plus, so only the first 30 will get the picture, get into the picture. Okay, we have few. We still need more. Come on, guys. Yes.
Rajesh sir has not turned on his.
Yes, Ashwin, thank you. So, so let's take a picture. In 3, 2, 1. One more. In 3, 2, 1. Thank you.
Okay. So thank you everyone. And remember, participation certificates will be provided to those candidates who fill the feedback form, which will be posted in the chat box after the vote of thanks. Now let's move on to the Q&A session. So if you have any queries on your mind regarding the topic, or if you have anything in general to ask the speaker, do feel free to unmute yourself and ask the question. And you may also put your queries in the chat box. You may ask your questions now, anyone? Okay. So I hope, since no one is asking anything, I hope everything is clear to you.
At least 7 plus participants. Please ask something. Okay. Anyone, please come forward and ask.
So there are some questions that are popping up in the chat box. Shall I go through them? There's only one question. The rest are comments. So Akhil is asking, is it true that the central black hole of the universe was there at the time of origin? So Akhil, I don't think there is a central black hole to the universe. In fact, the universe does not have any center. Okay, there is no preferred location in our universe. The universe does not have any center. I think what you are probably referring to, Akhil, is the central supermassive black hole. Well, the supermassive black hole in the center of our galaxy. So that supermassive black hole was not there at the time of origin of the universe. It came much later. But how galaxies form the supermassive black hole is a topic of very active investigation. There are no definite answers to this, but there are some strong hypotheses on how supermassive black holes form at the centers of every galaxy. Yeah, so Abhiram is asking, can somebody who has studied computer science engineering get into astronomy, astrophysics? Yes, it's very much possible, Abhiram. So in fact, there is hardly any field of science that does not require computer science. In fact, we are living in an age of algorithms. Big data is part of every scientific endeavor. Surveys like the Sloan Digital Sky survey, it pumps out terabytes of data every night, and analyze this data to extract meaningful information from this data, you need sophisticated algorithms. So astronomers are also good programmers, and if you have a background in CS engineering, then definitely astrophysics is a field where you can get into. You can foresee for yourself a career in this field. So the tools of the trade are physics, mathematics, and computer programming. Okay? So if you look at universities in India, institutes of national importance in India that provide doctoral education in astrophysics, like the Inter-University Center for Astronomy and Astrophysics in Pune, or NCRA, National Center for Radio Astrophysics, also in Pune, or IIA, Indian Institute of Astrophysics in Bangalore, if you go to their website, and if you look at the eligibility criteria for PhD admissions, they always say that they encourage engineering students. They strongly encourage engineering students to apply for their PhD program. So that means that clearly goes to say that a good understanding of mathematics, physics, engineering, computer science, etc., is going to be extremely helpful if you want to have a career in astrophysics. So yeah, by all means, it is open. Dr. Bindu has asked, what may be the reason for the disk shape of Milky Way galaxy? So galaxies acquire their disk shape because of conservation of angular momentum. So if you think of something that is collapsing and trying to form a structure, and if this initial collapsing material had a small net spin, okay, then as it collapses, as it shrinks in size and it forms a structure, because of conservation of angular momentum, it will start spinning faster and faster. Just like, in school, as we learned, when a figure skater pulls his or hand closer to them, then they start spinning faster. In the same way, a huge gas cloud, when it collapses under the influence of gravity to form a structure like a galaxy, it starts spinning faster and faster. And this spin would produce centrifugal forces that will push material away from the spin axis. So a disc-like structure will form as a result of this angular momentum conservation. Now, having said that, that is the reason why planets are all in one plane around a star. That is because when a star forms, material that is forming the star, it is also rapidly spinning. So some of the material, because of centrifugal forces, gets spread out in a disk, which is perpendicular to the spin axis. We know that is how planets form, and that is why planets are organized in one plane. For galaxies, it's not very clear why they have this disk shape. Is it because of the same reason, or there is something else underlying? So these are again topics that have been actively researched in the field of astrophysics. Okay, so Tamina Parveen is asking, do parallel universes exist? So Tamina, I don't think there is any observational evidence for the existence of parallel universes. The whole notion of parallel universe comes because of the fact that in quantum mechanics, which is the physics that talks about the universe at its microscopic scales, at the level of atoms and subatomic particles, at that level, the universe is known to be probabilistic and not deterministic. Now, what that means is that in the everyday life that we live, if we know certain parameters about the objects that we have around us, then we can predict how those objects will behave. So we can say with absolute certainty how those objects will behave if you know some parameters and with the help of laws of physics. But once you go to the microscopic world, as it turns out, nature in itself is not deterministic, it's probabilistic. So what that means is, if you are, for example, trying to predict the path a photon, a light particle would take or an electron would take, we can only say with a certain amount of certainty that it will go this way. There is always an uncertainty on whether it will go that way or some other way. So there is an uncertainty associated with not just our description of the universe at the minute scale, but the universe in itself is probabilistic. So this idea has led to the notion that maybe at the deep down, at a very fundamental level, it is possible for the universe to split into multiple multiverses or parallel universes at every point, and we tend to occupy one of those universes, and the rest of the universe we do not occupy, etc. So the genesis of this concept of parallel universe comes from this probabilistic nature of material at a very fundamental level. So Ashutosh Goel is asking, is string theory fully accurate? Sorry, Ashutosh, I do not know much about string theory to comment on it. It's used to describe fundamental particles and interactions between particles at a very basic level. But I do not know whether it's fully accurate or not. Okay? It's a faithful explanation of many of the phenomena that we see at a very fundamental level. But like most scientific laws, it's an approximation of the truth. Okay, every scientific law is basically an approximation of the truth. Science in itself is a successive approximation of the truth. So maybe there is some truth, and we are trying to understand it through using laws of physics and using the language of mathematics, and we are always approximating towards that. So in that sense, string theory is a very good way to explain many phenomena that we see at the microscopic level. So Sachit Sebastian is asking in the chat window, would there be opportunities to join the Indian Space Research Organization after completing MS in Astronomy and Astrophysics from IIST? So if you do BTech in Engineering Physics in IIST and then do an MS in Astronomy and Astrophysics from IIST, then you have an option to join one of the many centers of ISRO in IIST, provided there is a vacancy. Okay. But in addition to that, IIST has its own standalone master's program in astronomy and astrophysics. So if you do your bachelor somewhere else and join this master's program in astronomy and astrophysics at IIST, then this option to join ISRO is not there. But that doesn't mean that you cannot join ISRO. ISRO routinely recruits scientists through an outside examination, and you can always appear for that outside examination. It's called the ICRB examination, ISRO Centralized Recruitment Board exam. It happens every year. You can apply for that. But the pathway through IIST requires you to join IIST's dual degree program, BTech in Engineering Physics, followed by Masters in Astronomy Astrophysics. That is the pathway to join ISRO. So, yeah, so that's pretty much all the questions. There are some other general questions which I'm going to skip now. So Ashwin Jason is asking, do you have any of your own contributions in astronomy and astrophysics? So what I'm going to do now is, instead of boring you with all of my research, I'm going to type the URL of my webpage, my IIST's my official webpage. You can go and have a look at it. There I have described the research work that I have been doing for the past 20 years and for the past 10 years with students in IIST, and some of the research papers that we have been publishing over the years. All this is available on this webpage, which I have put on the chat box. Ashwin. So looks like I think we're done with all the questions. Then over to Akshay.
Okay, sir. So I hope all your queries have been answered. And right now, as a token of appreciation for Dr. Anand sir from our side, we would like to present him with a virtual memento. And for that, Ms. Shruti would be sharing her screen right now. Shruti will be sharing it right now.
Thank you, Shruti. Thank you, IEEE Kerala chapter for this wonderful momentum.
Okay, sir. And now let's move on to the vote of thanks. And for that, I would like to invite Dr. Lisha Paul, Vice Chair of IEEE ETSO Kerala chapter. Over to you, ma'am.
Good evening to one and all. Respected Chief Guest, Dr. Anand Narayanan, Professor, Department of Earth and Science, Earth and Space Science, IIST, and CM Varghese sir, EDSOC Chair, Kasim sir, Vice Chair of IEEE Kerala Section and founder of EDSOC, and Ajay sir, EC members, student coordinators, and dear participants. I express my sincere gratitude to Anand sir, who spared precious time from his schedule and enlightened all of us with 3D architecture of universe. Everyone is having much enthusiasm about the information related to galaxy and astronomy. Sir is presented in a nice and simple way. Normally, our webinar is webinar subject is technically related, and this is somewhat different, sir. That's why everybody is interested to attend this webinar, and it was very informative. And thank you so much, sir. I would express my gratitude to our EDSOC chair, CM Varghese sir and Kasim sir, for their valuable support and guidance in conducting this program. Also, thanks to all EC members for their constant support. Also, thanks to student coordinators for organizing such a valuable webinar. My deep sense of thanks and appreciation goes to all participants who were attended this webinar with great enthusiasm, made today's event a great success. Once again, thank you all.
Thank you, ma'am, for the vote of thanks. And now I have posted the feedback form in the chat box. So, and thus we have come to the end of our session. So once again, thanks to all the participants for actively participating in this event and making it a great success. We hope to see your active participation in our upcoming events as well. And don't forget to fill out the feedback form, which is posted in the chat box to get your certificates. Now, you may all leave the meeting.